Second speaker today is Nick Jones from Samsung Austin R&D Center, where he's a senior staff engineer. Nick's background stems from a lifelong love of learning programming languages to post-silicon lab debug and design verification. He's most recently been working on verifying an ARM-compliant custom CPU for SARC's next-generation IP. When he's not working, he's playing with his kids, triathlon training, or homebrewing beer. So all round to yours afterwards, Nick. As I say, Nick works at SARC, Samsung Austin R&D Center, and the title of his talk is Leveraging LevelDB for Unit Level Replay of Top-Level Stimulus in UVM. Over to you, Nick. Thank you.
Okay. Well, good afternoon, everyone. I'm going to try to go through this pretty quick. This used to be a half-an-hour presentation, so I had to cut it down quite a bit. Let's dive right in. So we'll start with a high-level overview about what am I talking about, how did I actually use this, the different data stores that I evaluated, how I landed on LevelDB, the test bench changes that we'll need to actually make this work, and then we'll talk about some concluding remarks. So leveraging DBs for replay. So as we all know, some bugs only ever happen at the highest level of integration. So the teams that I work on unit benches usually, and in this particular case, it was a tiny little unit bench. But some bugs were only happening up at the cluster bench. So I had all of the IPs that we were working on together, and it would only fail there, which is, kind of terrible because the unit bench runs so much faster. It takes a lot of time. I had the option of rewriting some of the stimulus that was up there as a directed test for unit. It was a constrained random environment for the unit mostly, so not a lot of directed test. It obviously takes a lot of time, and it only gives you a very narrow amount of stimulus when you do that. So I had a thought one day, what if I could just record what's coming into this design, this part of my design, from the top level and replay at the unit bench. So I could take that really long test that's up at cluster and rerun it at unit and board clean all the bugs that came out of it, and then rerun it at cluster again when it actually passed. So there was a nice side bonus to this too. I didn't realize at the time, but so if you have this really awesome seed at unit for constrained random that generates something interesting, now I have the facilities to also record that and turn it into a directed test. And oddly enough, it actually goes a whole lot faster than a constrained random solver, at least with the simulator we were using at the day. So it was about 5 times faster. So it was a pretty nice uptick in performance to do that. So what does it look like to capture these things? So the premise here is that we have an integrated UVC. So my unit's UVC was instantiated up at the integration level benches, so at CPU and cluster. So all of the monitoring and everything else was all there. So typical UVM, thinking the words are escaping me. But so I have all the sequencer agents and everything else up there, but basically in a passive mode. So all the monitors are still alive, checks are still alive. And you make sure all the ports are actually monitored. So everything interesting for this particular unit at cluster need to be monitored by my UVC. I also needed sequence items that were emitted from the monitors every single cycle, and we'll get a little bit into why that is later. I know that's not particularly common in UVM, or it's kind of frowned upon, but for this to work, you do need that. And at the lower level, we'll leverage the UVM pack interface. So every single UVM object or descendant from it has a pack and unpack method, and we'll get into what that means and how it works. So how do we do this? So from each monitor, they all do AP port writes for each one of these sequence items. I showed them through an analysis FIFO in the thoughts that maybe the DB would get a little behind and it could do multi-write in a single cycle if it needed to, but that's not actually required. So on the other side of it, I wrote this class called UVM Custom Recorder. And what it does is it takes a sequence item, and it's actually typed with whatever item you're interested in, and we'll call pack, and then basically put it into the DB for you. That's kind of the guts of what it does. It's pretty generic. It doesn't really understand what the item is about or how it works or what its meaning is. It just knows that I take one thing from one side, I do some operation on it, and I put it into this other side through DPI connection. And we can do this for every single monitor that's out there in the UVC. So what replay looks like is within our virtual sequence, we'll connect into our data store. In this case, it'll be LevelDB. And we'll retrieve each object. And again, we'll go through a typed class that is of the type of the object that we're trying to reconstruct. And through that, we will unpack, through the UVM method, the serialized data that we have in the data store back into the object, and then send it along to the sequencer like you normally would. There's a bit of a caveat here that the driver does need to do some special behaviors or be less smart than usual if you like writing smart drivers. And you'll need one of these for every single kind of item and driver you have on the block. So there were some special cases about this block, and we'll get into the caveats in a little bit about why this worked for this. It may not work for all cases. So the use case, an ETM. Probably most people are not familiar about what an ETM is, or embedded trace macrocell. In ARM architecture, there's a widget that they architecturally define that monitors microarchitecturally what's happening from a program execution perspective. So how you're retiring instructions, taking exceptions, branching, that kind of stuff. And it turns it into trace level packets that go out in a TB interface, so AMBA trace bus. And these packets that go out represent the state of the machine, so the context, what exception levels you're at, or what security levels you're at, and different directions they're changing in the program. So as you take a jump or whatever, or branch, then you actually get a packet that represents that and tells the debug software on the outside of the world where the core is going. So there's two register interfaces. There's an internal one, so you can, through assembly, program this thing, and through the outside world on the AMBA peripheral bus, APB, you can also program it. So there's two register buses, both have access to everything. And they're kind of sideband to the retire interface, which is hooked up microarchitecturally to all the retire units and other stuff inside of the core. So what broke? So as I mentioned before, I had an awesome stream of random instructions up at cluster that found some quirky behavior in ETM. So retire did some things that we didn't know it would do, but we realized were okay from a design perspective in the core. But it broke some assumptions on the ETM side. So we had to redo some things, and it kept breaking. So the same test, you go a little farther and break again, go a little farther and break again. And each one of these times, we kept hitting something that we thought we could hit in a constrained random environment at unit, but we just weren't. And so the thinking was that the probability was just so low that we'd get these back-to-back kind of behaviors that we just weren't hitting it. We could have spent a bunch of time actually trying to retune the stimulus at unit to go after these special cases, but with replay in mind, this gets a lot more interesting with a lot less work. So as you know, the iteration of debugging at this level takes forever. So the compiles are longer, the runtimes are longer, and as you work through a single test, and that single test goes farther and farther and farther, and that takes you even longer to get to a failure. So it's kind of hard, especially for a guy who works at unit. So we introduced replay. So I couldn't believe it actually worked initially. So I recorded this test with all my checks turned off up at cluster, and saved it all, and then replayed it all at unit. I was actually able to get the exact same failures at unit. So the first one, I took the RTL back to its broken state and checked that it actually broke there, and then we put the fix back in, and then it broke at the next bug we found at cluster. So I was tracking with the bugs that we were finding. This got our cycle time down a lot because the unit bench was substantially faster to compile. I think it was only a couple minutes to compile, and then the run times obviously are a lot shorter as well because it runs a lot faster. So it was a pretty big win to reproduce all these failures and take all this stimulus from above and bring it down to the unit bench and make this work. So how do I do this at speed? So so we got to go through this a little bit quickly, but there's three different choices I kind of looked at: a SQL solution and a key value solution. I wanted all the simulations to be separate from each other. That was kind of a big thing for me. I didn't want thousands of cores right into a single database server. And I wanted 32-bit support because we were seeing about a 10% performance uplift when we ran 32-bit. So SQL versus key value, I'm going to kind of breeze through this real quick. There's different ways of storing data. SQL is a lot like a spreadsheet where the monitor is the sheet, and then each of the fields, the ID and data would be columns you have in that spreadsheet, and you add rows. And you can ask the spreadsheet, if you will, to count up how many things you have. In a key value store, you need to make a composite key. So you have to pack together the sheet name or the monitor name along with which transaction number this is and put it into the database. And I'll also have to store the total so that we can get it on the other side. And then we'll go retrieve each item as we iterate through a for loop. So the 3 DBs that I looked at, as I mentioned, SQLite, super simple, tiny footprint. So that was kind of cool. LevelDB was written by Google, supposed to be pretty fast with key value store. And RocksDB was written by Facebook, taken on from LevelDB, and it's supposed to be even faster. So let's look through the evaluations of these pretty quick. So the SQLite one, unfortunately, was so slow. It was actually a whole lot slower to record it than it was just to debug it at cluster. So that was out. So I tried RocksDB, but as I got into it, I realized it lacked a 32-bit compile. So I was going to drop 10% performance already with that, and that's kind of rough. So I backed off to LevelDB. It actually had really good performance and met all my requirements. So what does it look like to pack these things? So we'll get the item from the FIFO, and then we'll call the UVM pack bytes, which turns it into a dynamic array of bytes for us. And we'll have to iterate through that array and turn it into a string, because that's the API for LevelDB. And then we go through the DPI layer, passing the string of what is the composite key and the value. Then we iterate and grab another one. So really simple, and this class doesn't understand what it's, what the item is. It doesn't have to care, which is also kind of cool. On the unpacking side, this method will get called by a sequence as it to go through and unpack all these items. So we'll retrieve a key from above. We're basically told what the key is, and we're passed a reference to an object. So the last level would be, hey, go get this thing. We need to do a little bit of work to convert string types. So LevelDB speaks in C++ strings. So we actually get a handle to a string. We convert it to a char star, which is a C string, and then free the string on the C++ side, the standard string. So just a little bit of hand holding there. And all of this code and everything is in my original slide paper, so I don't feel like you have to write it all down really quickly. Then we get our string back, so now we have to turn this back into a dynamic byte array. So we'll unpack these bytes, or deserialize these bytes, if you will. And then we'll call the UVM method to unpack them back into the object. And this is what will actually put all the fields back where they were and reconstruct the contents of this object. So in replay side, so what we'll do is we read the total number of stored objects before we get into this loop. And then we'll just iterate. So it's real simple. You do a create, you start the item, and then you unpack the object from the database back into itself, call finish item, and then you shove it off to the driver, or off to the sequencer, which then sends it to the driver. The driver, you have to be careful. It has to be it's really dumb in this way, that it needs to just do what it's told. It needs to just drive the interface with what it's given. I tend to write really smart drivers, so the sequences are less of a interface protocol type thing. They're more of like how should it operate at a higher level of passing packets or transactions or whatever. So this needs to be a little bit more of a dumber mode. So what happened? So as I mentioned, reproduced all the original failures and got a substantial performance improvement. So rerunning the recorded stimulus from cluster down at unit was 30 times faster. So it saved us a ton of compute time, saved myself a bunch of time. And it actually was accurate clock to clock as you looked at waves. So it was pretty cool. There was a slight staggering between two different interfaces, so the register interface and the retire interface. But I ended up fixing that later on. This was future work at the time. But to get perfect coordination, I ended up instantiating a new agent that actually looked at the entirety of the inputs to the ETM itself. So I had all the retire interface and on all of the register interface. So that got everything lined up for the tests that the register writes had to be timed with the retirement instructions. Let's see. So as I mentioned, a whole object. Oh yes, I didn't do anything with multiple clock domains. So this is all a single clock domain environment. So I didn't touch the MCP space at all as well. So there may be some pitfalls in there. And then lastly, thank you. I apologize.
Thank you very much.
Real fast. Yeah, sure.
Yeah, that was real fast. Thanks again, Nick, for doing that. You're actually solving a problem that I've encountered many times.
Oh,
it's
nice.
easy to you want to generate. It's much easier to generate stimulus at the CPU level. And then you want to debug down at the unit level. So that's
yeah, there's a lot of code generators out there that was pretty helpful.
Yeah, very good. Looking for questions, none from Bristol, and none online. So thank you very much, Nick. And will the full set of slides be available or not, or is it just the condensed?
I recommend going to the SNUG website. In the 2016 proceedings, you'll find me under the verification track, and you'll find my full slide set, and there's also an audio recording of the presentation.
Perfect. If you share that link with Sarah, then
Will do.
okay, brilliant. Thank